So, wrapper preload instruction, the WS preload instruction, so that can also be used. So, in this case whatever so it is a serial preload. So, if it is serial preload, then whatever is coming in the WSI line, so that is actually loaded into this WIR register. So, that way rest of the thing is not active. So, so the serial control will be loading this say this WIR register. Similarly, this parallel control can be used to load this WBR registers, but the whole thing is the preload operation. So, it is not sent to the core under test. So, this is basically that R1 flip flops of all these WBRs, WBCs. So, they are actually configured into chain and they will be loaded the values. So, this WPO, so WPI, WPO lines. So, these values will be loaded as a preload instruction. So, then there is a parallel preload WP preload operation. So, this is again the same thing, the WSI will be put into the bypass mode. So, this wrapper serial input is not going to affect this WBR. So, that is going into bypass mode, and this whatever has been loaded into this WBR. So, they are available as preloaded state. So, similarly, this WBR content is also available as a preloaded state. So, whatever values were preloaded, so they are available at the output of those parallel outputs. Then there is a clamp. So, clamp means that this WSI and WSO lines. So, those values have been applied, but this is they are applied to functional input and functional output that passes through this core. Actually, the functional inputs that are available at WBR, so that is passing through the core. Similarly, so they are affecting the functional output, and then these functional outputs are loaded onto the WBR. Actually, this direction should be reversed. So, Fi should be this side, Fo should be that side. So, anyway, so this is basically this the pattern passes through the core, the clamp mode. Then the in-test mode. So, in the in-test mode also it is similar. So, this wrapper this boundaries registers, wrapper boundary registers, so they are going to be connected through these internal scan chains. So, they are in the previous case only functional input and functional output were involved. Now, these internal scan chains are also involved. So, internal scan chain will get the values, and accordingly those this core will get the full set of inputs, and that will be passing through these WBRs, and then the values will be available at this WSO line. So, the serially this WBR values will be available in the scan out lines. In-test scan. So, in-test scan means here the functional inputs will not be fed, but this WSI line. So, they will be passed, the scan chain will be formed, the scan chain. So, it will pass these lines through these scan chains. So, this is basically for checking the boundary scan register. So, some pattern that we need to pass through this scan chain to see whether these scan cells are okay or not. So, these boundary scan cells are okay or not. So, some pattern may be fed through this, and that will check the scan part. So, this the scan chain part will be tested. So, that is the scan instruction. Next, we look into what are the possible test access mechanism architectures that are there. So, we have got this serial input. So, core has got a wrapper, it has got one serial port and a parallel port. So, there are two such ports. Now, this scan the serial input that is coming. So, it can go through this it will go through this serial interface, and these parallel inputs they will go through this parallel interface. So, this WSP register, the serial port register or the serial port interface, it will have an enable line to the parallel port. So, at least through this WSI line. So, we have to give some instructions, so that this parallel loading or parallel operations are enabled. Okay. So, that is why the serial part is mandatory of this 1500 standard, but this parallel part is not mandatory, but parallel part may be used for doing the loading. So, this WPI, WPC, WPO, so these are the parallel parts. So, how these will be connected? So, that is determined by the user, how these WPI, WPO lines of individual codes they are going to be connected, whether it is on a bus, whether it is some distributed lines, etc. So, all those will be decided by the user, but whatever it is, then that loading and unloading has to be enabled by the serial interface. So, that is why the serial part is must. So, one possibility is that we have got a multiplexed TAM architecture. So, multiplexed TAM architecture means out of this this WPI, WPO and WPC lines. So, they go to all the places, like this WPI line is going to all the 3 core interfaces. This WPO line, they are coming out of all these parallel interfaces and going to the WPO line, and this WPC line. So, it is going to the again going to control individual wrapper, parallel wrappers, the parallel part of it. Whereas, this WSI line, so it is connected to serially one, and this WSC, the control line, so it is going to control this WSP, the serial part interface, and naturally there has to be some control for that, control for this WPP from the WSP. Now, at one point of time, so you can test only one core, because they are multiplexed in nature. So, so we do not need large number of inputs, only so whatever be the WPI value, only that much bit is needed for sending in the test pattern, and similarly for getting out. So, you can say that altogether we need WPI plus WPO number of bits for the test bus that we have, and the multiplexed TAM is this WPC lines will also be necessary, but that is the maximum line that you are going to allocate to any of these cores. We can have some sort of daisy chain structure. So, WPI line interfaces the first core, then this WPO line of first core connects to the WPI of second one. Now, if you put them in a bypass mode, then this WPI line will be going through to this one, then it will go to this WPI of second one. So, it will go like this. So, this particular architecture is known as daisy chained TAM architecture. So, we have got this daisy chained policy, and then of course, it takes time. So, for testing this core, it has got the highest priority. Whenever this core test is scheduled, so it will happen immediately, it will get the WPI line. Similarly, if it is so I can test this core only when this one is not being tested. Similarly, I can test this core only when the first 2 are not being tested. So, their test scheduling become constrained by this TAM architecture, whereas in this previous case, so since it was multiplexed, so I can do multiplexing in any order. So, I can if the cores they support preemptive testing, in the sense that I can apply, say one core require 100 test patterns. So, I apply only 50 of them now and 50 of them later. So, that type of interleaving, if it is possible, then also this multiplex TAM is going to help. But here in this case, once a test is going on, so nobody else can be tested. Okay. So, that is the problem with this daisy chain structure. Then we have got this is the most flexible structure, the direct access TAM. So, this WPI, WPO, WPC lines, so they are dedicated for every core. So, they are given separately. So, this triple WPI, WPC, WPO is for core 1, this is for the second core, this is for the third core, like that. So, naturally here the advantage is that the number of ATE channels needed will be large, because a large number of bits will be are to be fed for testing, though we can do parallel testing, but a large number of bits need to be fed to the circuit. So, as a result, we have got this the ATE cost will go up, but test time we can say that it will get reduced. We can also have some sort of local controller for TAM architecture. So, it says that okay, we have got so this controller, so this controls this operation. So, this TD this WPI, WPO and this WPC line. So, they may be controlled by this local controller. So, we can maybe from a global point of view. So, we can give instruction to these controllers to operate, we can give some top level command to these controllers, and then these controllers, so they will give commands to the they will control the actual test session. So that can be done. So we have got this type of local controller TAM architecture, so that can be utilized. We can also have some sort of core access switch. So core access switch means, so there is a test controller, so it will pass this access of these WPI WPO lines into these switches. Okay, so through these switches. So if this switch is done, so there are n lines coming from the test controller. Some part of it is for selecting the switch, and some part is actually that those TDI TDO lines. So once this switch is on, so this connection will be to this core. Similarly, when this switch is on, then this connection will be to this core. So we have got a controller, and there is a there are a number of switches, core access switches, through which this control will be, this access will be controlled. So that is the core access switch. So this core access switch, so it can be operating in the configuration mode. So here in the configuration mode, what happens is that the instruction may be loaded. So now the core is not being tested, but only the instruction is being loaded into the instruction register. So this configuration the configuration selection point, so it can say, it can select that it is now putting the data onto the configuration onto the instruction register. So this configuration bit can be controlled accordingly, so that instead of the pattern reaching the core, so they will be reaching the instruction register only of the wrapper. Now in the bypass mode, so they are just bypassed to the output. So this parallel input, so they are outputted here. So that is the by simple bypass mode, or it may be in test mode. In the test mode, maybe I will apply the first test pattern, get the response. Similarly, so this first bit is going to connect to the first input. Then maybe for this particular core testing, only these 3 lines are important. Similarly, say only these 3 lines are important for output. So rest are not. So rest of them may be passing directly through this switch, but we can have only these 3 lines feeding the core that we have downwards. So this some of them are input lines, some of them are output lines. So input lines will be connected to this, output lines connected to this. So as a result, the whatever test pattern has to be applied, so it will be applied, and the response will be collected on these 3 lines. So remaining 3 lines, remaining 2 lines, it may be used for testing another core simultaneously, or so depending upon our scheduling policy, so we can select those lines. So there can be various types of tests supported using this CAS structure. Now one possibility is that I have got a core that has got scan chains. Suppose there are p number of scan chains. So from these n lines, so p bits are to be used for feeding this scan chain. Okay. Now this particular second core, it may be a beast structured core. So from this input, I need to I just need a command that it has to have the it has to go in a beast fashion. So it will generate its test patterns in a from the test pattern, some pseudo random pattern generator, and response will get analyzed by MISR. So all those things are all those things will be done by the beast that we have integrated with the core. Thirdly, so this core maybe it has got its own test pattern generator and sink loaded with it. It may not be a beast. So beast may be using a pseudo random pattern generator. So it may not be using a pseudo random pattern generator. So it may be some specific pattern sequence that is generated by some hardware, maybe stored in some memory there, or maybe generated by some hardware. So that is generated, applied to the core, and the response is collected at the sink. So that way we can do this thing. So this is the core access, this is the core access switch. This can be configured so that it will be feeding this source. So again, maybe only one bit is necessary to tell the source that okay, this is the thing. Similarly, this sink the pattern will be, response will be collected. it may be shifted serially, or maybe the final compacted pattern will be shifted. So, that way it can be done. And another possibility is that it may be a hierarchical structure. So, instead of having a single core, there may be 4 cores, for example. So, here also I have got this type of core access switches available with these individual cores. So, there may be the line connected the first switch, that switch may be connecting to the other switch. So, that way it may be connected, and finally it is going out of this core and going to this line. So, what happens is that this core this ATE has given us n bit for coding this pattern, for coding the operations to be done at various places. So, if we can judiciously do a planning, we can judiciously do some test scheduling, so that I can use p bits for feeding this scan chains, I can use 1 bit for feeding this one, again 1 bit for feeding this, and again p bits for feeding these CAS lines. So, that way I can be able to test a number of modules parallelly, because they are using different testing mechanisms. So, I can use them parallelly, and I can get a faster testing of the whole chip. Next one is a hierarchical test architecture. So, this is basically this is a typical situation. We have got this course supporting this 1500 series. So, they are called C tag cores, because they are supporting this core interfacing. So, they can be directly connected to this, they can have both serial connection as well as parallel connection. So, they can be connected through this TDI line serially, or they can be connected with the TAM bus. Okay. So, the both of them can be used. Then this there may be some cores which are not which are not compliant to 1500. So, if they are not, so they may be supporting only 1149.1. So, that is only the boundary scan standard is supported. So, if only boundary scan is supported, so they have to be connected to this serial input part. Okay. So, serial testing and all that are to be done. And there may be some cores which are hierarchical cores. So, hierarchical cores means they are they have got some cores which themselves are SOC. So, they have got their own test architecture embedded, and then for those cases it becomes more complex. So, there may be the test patterns are available through this serial input, as well as this test access mechanism also may be having this thing. So, this way we can have this whole chip consisting of different types of cores. So, different types of cores from the viewpoint of their compatibilities, and that way we have got different types of cores, and it is like this. Now, so this is forming my TAM bus. So, this is forming my serial TDI TDO serial interface, and there are some test control lines. So, that will be coming to the CTC, and there is a hierarchical control line. So, that will also be coming to CTC for the control operation. So, this way if we can support all these modes, all these interfacing standards, then we can go for a plug and play type of architecture. So, any new core that we want to put into the system. So, if it is compatible with say 1500, maybe we will like to test it using TAM. If it is not that, so we may like to test it using boundary scan. So, like that, depending upon the interface supported, so we can go for that. And plus this glue logic, so they are also to be tested, but the glue logic, they are discrete gates, discrete flip flop gate like that. So, they do not have any compatibility with these standards. So, they are to be tested in a different fashion, and this system integrator actually has to bother about how to test this glue logic part. Okay. So, that may be by means of some extra X-test mode and all that. So, this is the hierarchical test structure, that this may be one possible hierarchical test structure. So, we have got this hierarchical core. So, hierarchical core, it has got its own CTC, the control test control point, and it has got this TDI and TDO lines connected. So, this will be this may also connected to this test access mechanism. So, inside it will generate its own hierarchical hierarchical test information. So, it has to control the individual 1500 or this 1149 interfaces of its own individual codes. So, that is not shown here. So, that has to be done, and this programmable switch. So, it can be there is a test access port and there will be a hierarchical test controller. So, both will be there. So, this hierarchical input, so they will be coming to this hierarchical test controller, and this tap control signals. So, they will be coming to this tap. So, accordingly this part will be controlling this individual TAMs and individual codes which are supporting this 1500 and 1149, and this has to be done at a more detailed level. So, by breaking the signal, so it has to do its own scheduling, it has to do its own TAM distribution, and all those things are to be done. So, that depends on what type of codes we have inside this high level code. So, if we have got a hierarchical test architecture with IOs compatible to 1149, so that means it does not have this 1500 interface. So, here this is this is the hierarchical code that we have. Now, this core 3 and core 4, so these two cores, so they do not this core 3 core 4, so they are CTAG codes. So, they are supporting this hierarchy. So, they are 1500 compatible, but this core 5 is JTAG compatible. So, it is 1149 compatible. So, in that case we have to this hierarchical test this HTM1 top level one. So, it has to put some of it since these cores are supporting 1500. So, it has to it can design its own TAM at this point, and it can distribute these signals as it was done here. But for this one, it has to give the the data through the serial part only. So, this is this test access port. So, this is a serial port. So, it has to get its own TDI line, then TDO line, like that. So, it has to get it from there. So, you see that this TDI line, this TAM in this TAM input line, what is it? Yeah, this TAM input line. So, it goes to this TAM, and then it is put onto this boundary scan also. So, it is coming here, then it is going to this TDI for the core, test data input for the core. So, it comes here, then this is daisy chained like this, and then this line, this TDI input goes to this one. So, that way this TD, so this is the daisy chained structure, and this TDO line of this core. So, it may be put directly onto the TAM, or it may be put onto this flip flop chain again to be taken out and going to the TDO. So, that way this to the TAM output. So, that can be there. So, it may be coming from here, or it may be going from there. So, the thing is that the cores within a hierarchical core, we may have some cores which are supporting 1500, whereas there may be some cores which do not support this 1500, they support only JTAG. Some of them may be B-state, some of them may be 1500 compatible. So, this way this whole distribution, this TAM design has to be done, so that it is taking care of all different types of modes that are there. To compare between 1149.1 and 1500, so 1149.1 is a board level, it is targeted to board level design. 1500 is for core based design. So, that is the first difference that we have. Secondly, this 1149.1 it supports a parallel mode of operation, whereas 1500 it does not provide any 1149.1 it does not have any parallel TAM structure. 1500 has got parallel TAM structure. Then this extra data control and IO lines. So, they are the mandatory lines are TDI, TDO, TMS and TCK. Optional line is TRST. Whereas, for 1500 we have got WSI, WSO and 6 W scan control lines. So, they are required, and this transfer DR, WPP and auxiliary clock. So, these are the optional lines. So, it has got an FSM that can be used for controlling the operation, but 1500 does not have any such controller FSM. Transfer mode is not available in 1149, but it is available here. Latency between operations are permitted in 1149, but it is not so, and these are the mandatory instruction, X-test, bypass, sample, preload, and these are the instructions that we have for 1500. We will continue in the next class.